So it occurred to me as I was working out this problem for everybody just now that I think some of the reason why people are uncomfortable with solving for the packing efficiency of a face-centered metal is that we attacked this problem using trig identities. And if it's been a while since you've had trigonometry, then I can see how this could be a little intimidating. Or maybe you've never had it, or maybe it was a really long time ago, who knows. So I thought that I would show you how to solve this problem without using trig functions, without using sine or cosine. We're going to instead solve this problem, this portion of the problem, by using the Pythagorean theorem, which, if you'll recall, says that for a right triangle, a squared, one side of the triangle, plus b squared equals the square of the hypotenuse. You can use this to solve for a in terms of r the same way that we just did here. So I'll walk you through that in case that's a more comfortable method for you. Alright, so let's consider, we're just going to consider this triangle here. Alright, each side is a. Again, forgive me, I'm not to scale. The hypotenuse is 4r. So when we write our equation, we've got a squared, one side of the triangle, plus a squared, the other leg of the triangle, equals 4r squared, or 16r squared. Okay, so let's see if we can solve for a. 2a squared equals 16r squared. A squared equals 8r squared. A equals r square root of 8. And if you remember how to work with square roots, this is the same thing as 2r square root of 2, right? Because 8 is 4 times 2, and you can take the square root of 4. So this becomes 2r square root of 2. A cubed equals 2r square root of 2 cubed, or 2 square root of 2 cubed r cubed, not squared. 2 square root of 2 cubed, r cubed, and look, same exact thing. So if using the Pythagorean theorem here is easier to understand for you, use the Pythagorean theorem. If using trig functions is easier to understand, do that. Either way, you should end up at the right place at the very end.